Our default intuition treats order as a one-dimensional sequence. Think of a timeline, a leaderboard, or a sorted array. We assume that to organize information is to place it on a line. This assumption fails when data is defined by multiple, simultaneous constraints. A dependency graph for a massive software project or a system of overlapping subsets cannot be reduced to a single sequence without losing its internal logic. When this multidimensional structure is compressed into a timeline, we force a ranking onto elements that have no actual relationship. We create a false hierarchy. This requirement is the totality axiom. It demands that for any two elements, one must be larger, earlier, or more significant than the other. Real systems are rarely total. In a distributed network or a causal chain, two events often exist without any sequential link. They are simply incomparable. Engineers and data scientists often interpret this incomparability as a failure of measurement, an error that a more sophisticated sorting algorithm should eventually resolve. Flattening these relations into a line is a lossy transformation. It erases the structural dependencies that make the data meaningful in the first place. Partially ordered sets, or Posets, provide the mathematical alternative, governed by three axioms: reflexivity, where elements relate to themselves; anti-symmetry, preventing mutual superiority; and transitivity, ensuring logical consistency. By omitting the totality axiom, the Poset allows structural incomparability to exist within a rigorous framework. Consider positive integers ordered by divisibility. While 2 is less than 4 because it divides 4, the numbers 2 and 3 are incomparable. Neither precedes the other in this specific relation. A total order imposes a comparison by default. A Poset acknowledges only the comparisons earned by the underlying logic of the system. In this framework, the absence of a relationship represents a precise state of independence or concurrency. We can analyze the internal architecture of any Poset by breaking it into two primitive components. The first is a chain. This is a vertical slice of the Poset, where every element is comparable to the next. It is a local island of linearity. The second is an anti-chain. This is a horizontal layer where no two elements can be compared. It represents a state of total mutual independence. These two structures allow us to quantify exactly how nonlinear a system is. Dilworth's theorem establishes a formal equivalence between these two measures. To find the width of a Poset, we identify the largest possible antichain, the maximum number of elements that can exist without any relative order. We then determine the minimum number of linear chains required to cover every element in the set. Dilworth proved that the minimum number of linear threads needed to cover the entire structure is exactly equal to the width of its largest antichain. Mirsky's dual theorem provides the inverse. The height of the longest vertical chain dictates the minimum number of antichain layers required to partition the set. Nonlinearity is not a flaw. It is an exact, measurable tension between longitudinal threads of dependency and transverse layers of independence.
In computer science, the process of pulling a complex dependency graph into a single permissible sequence is called a topological sort. This creates a linear extension, a schedule that is compatible with the Poset, but adds information that wasn't originally there. Because the line requires totality, the algorithm is forced to assign a sequence to elements that are actually incomparable. Mistaking this arbitrary execution schedule for the underlying causal structure is a category error. One is a choice, the other is a constraint. Dushnik-Miller dimension theory measures this gap. It asks how many different linear extensions we must intersect to perfectly reconstruct the original Poset. This number is the Poset's dimension. It represents the number of linear perspectives required to fully describe a multidimensional order. The Poset is the invariant geometric structure that exists behind these one-dimensional shadows.
While we often visualize Posets as discrete graphs of dots and lines, they can be translated into continuous geometric shapes. The order complex provides a rule for this transformation. Every chain in the Poset is treated as a face of a geometric solid. A two-element chain, A to B, forms a line segment. A three-element chain, A to B to C, defines a solid triangular face, or a simplex. Because these chains overlap and share elements, they weave together into a continuous geometric manifold. This means we can apply the tools of topology to a simple list of rules. We can measure the holes, surfaces, and connectivity of a system of constraints to understand its global shape. A finite skeleton of logical relationships produces a continuous geometric object. In high-stakes environments, like distributed networking or complex multi-parameter data analysis, forcing a line creates severe logical failures. Distributed systems rely on Lamport's causal order, where events are linked by influence, rather than a global clock. The network is a poset, not a timeline. Two events that cannot influence each other are space-like separated. They form an anti-chain, existing independently in a way that no single observer's clock can fully capture. In machine learning, evaluating a model on conflicting criteria produces a Pareto frontier, a glowing anti-chain boundary resisting a single access. To get a single score, scalarization crushes these dimensions into one number. Preserving the poset visualizes the true trade-offs this hides. Across physics and computation, the poset provides a mathematically disciplined way to resist the drive toward oversimplification. A total order is a special, simplified case of a poset, one where incomparability has been systematically eliminated. Timelines and sorted lists are useful tools for coordination and consensus, but they do not reflect the fundamental structure of complex information. The line is always a reduction, a specific projection, or a lossy compression of a much deeper field of constraints. When order is no longer bound to a line, incomparability functions as structural information rather than a missing measurement. The goal is not to erase these gaps through forced sorting, but to understand the profound geometry they define.